I would like to let you know is that in many cases, letters and symbols and also numerals are what we call character. Why? Because for what does it mean for numerals? Okay, for example, the student ID is the numeral. We usually use this as because of this is a number, but we usually don't want to use it to calculate anything, right? So we call it numeral. Okay, for something is a number that, and we are not going to use it for calculation, it's called numerals. Remember this. Okay, and then the second part is that we have different types of codes usually used. For example, we have the ASCII code and also extended ASCII. What are the difference between these two? Okay, let's see. First of all, for ASCII code, it's something like that you can input in the keyboard, right? And how about for the extended ASCII? That means there are some characters that you cannot find in the keyboard, but you would like to type it. This is what we call extended ASCII. Okay, so what's next? Show my hand. Yeah, this is extended ASCII, and what's more is that, and also, for example, in your window, when you click on the what we call character map, okay, character map. How can I call this out? It's very easy. Just type CHAR, and then you can have this out, okay? And then you can click on whatever you like. For example, you like pipette, you can also click on this to have a pipette. Okay, it's easy. Got it? And also, you have many other, like this one is yeah. Do you know the difference between these two? One is female, one is male. Do you know which one is female? Okay, I think it's easy, right? Yeah, I think I can introduce why this is boy, because for boys, sometimes they would like to eject something out, okay? So eject something, so the arrow is pointing here, okay? Got it? Okay, so you can type any extra character over here by using, for example, extended ASCII. Yeah, after you copy this, you can paste it here. Got it? Of course, some of the characters that are not included in the extended ASCII, we are going to use other coding. Okay, so think about this. For 7 bits, okay, we usually is from the ASCII code. Okay, and 8 bit is for the extended ASCII. So can we use 8 bit to represent also ASCII code? Of course we can. We can add the 0 at the beginning to represent this. If you would like to change from 7 bit to 8 bit, okay, it's easy. So something like you have here 0, 1, 1, 0, 0, 1, 0, 1, representing the A. Originally 7 bits is already okay. Got it? Once again, 7 bits is already okay. But now, okay, what the problem? But now you have a preceding 0 over here. That means you add 1 0 at the beginning to make it to become 8 bits. Got it? Okay, easy. Okay, so let's see here. For example, I type 65. Oh, I'm wrong. 65 over here, it should be like 0, 1, 0, 0, 0, 0, 0, 1. Okay, that means it's A. Got it? Easy. Okay, okay, how about the last one? Last one is a 1, 2, 6. Okay, that means it's this one, 0, 1, 1, 1, 1, 1, 1, 0. It represents the curly wave, okay? The wave over here, okay, easy. Okay, I think all of you know this before, but I would like to introduce two more. Is that the 10 and also 13 is what we call line fit and also carry return. Line fit, that means to go to the next line. Carry return, that means after you go to the next line, you go back to the first character. Is carry return. Okay, what's more is the space. 32 is the space. Okay, space is also one of the character. Remember this. Got it? Okay. Okay, once again, line fit is to go to the next line at the same position. Okay, but for carry return, we go back to the first character of the next line. Okay, got it? It's easy. For example, something like you are typing here, your car, I'm so cute, something like that. So if I press the fonts, like for example 24, okay, so you go to here, that means you go to the next line. That means just line fit. If I go back to the first letter, yeah, that means it's carry return to the first position. Okay, like this. Go back to the first position. It's what we call carry return. Got it? Okay, easy. Okay, so this is what I would like to share. For Windows, we usually use both CR and LF. In program code is \R and \N to have this action. But for Unix and also Mac machine, we simply use line fit and it will already return to the first letter position. Okay, they are the difference between different systems. Got it? Okay, what's more is that we are going to learn is the Unicode. What's that for Unicode? Unicode is 16 bits character. Oh, so many, yes. Originally, English, that means ASCII code or some symbol, only use 8 bits. Okay, but Unicode we use 16 bits. Just now I mentioned LF is a line fit. Okay, that means go to the next line. Okay, it's called line fit. Got it? Okay, so let's see what are the difference. Yeah, ASCII code is 7-bit, extended ASCII is 8-bit. How about your Unicode? Okay, let's see. Yeah, once again, for ASCII code, in fact, you have no need to add the 0 at the beginning. But in hardware, we usually need to handle 8-bit at once instead of 7 bits. Once again, this course is to tell you how to implement something in hardware, right? So we also need to treat the ASCII code into 8-bit by adding the leading 0 over here. Got it? Okay, for example, for Unicode, what are the usage of Unicode? I remember the author of the Unicode said that he has a dream. He would like to incorporate all the wordings in the world into one code. Okay, this is what he believed. So he invents a Unicode. Got it? He invents a Unicode. And so, for example, every Chinese word, every Japanese word, no matter which country's word, you can also use Unicode to write here. Okay, for example, the Unicode for 你好, 你好咧, 我講廣東話咧. Okay, it's a 6088H. Okay, why is 16 bits? Because each hexadecimal letter, each hexadecimal digit can be represented by 4 bits. Okay, so 4 hexadecimal digit. That means how many bits is multiplied by 4? Okay, because each digit need 4 bits to represent. So we have 16 bits together. Got it? So 你咧就係60 is 6088 in Unicode, and 好咧is 5970 in Unicode. That's it. Got it? So Unicode is our future. Okay, so yeah, because it's 16 bits, so it requires 2 bytes to represent this. Got it? So now that no one will use other code. Yeah, if they would like to represent all the wordings in the world. Got it? Okay, so finish for this part. Okay. Yeah, for Unicode is not only Chinese wordings. They can also include Japanese or whatever every country's wordings in the world is also okay. Got it? Okay. So let me stop the recording first. Okay. Okay. So next part I would like to introduce is that okay. Yeah, next part I would like to introduce is that lecture 2 Boolean algebra. Okay, so what's that? Yeah, we're going to learn some not operation or operation and operation, etc., etc. Got it? Okay, let's see here. For example, yeah, how can we represent the symbol for the NOT gate? Okay, it's easy. We have the triangle and then we have the circle here. Every time we have the circle alone can also represent NOT. Got it? Okay, it's easy. Okay, so here we have, yeah, for example, this one, we have A here. So after this circle, that means we have NOT A. Okay, so it's easy. So we have the symbol like the bar, we have the A, or you don't like the bar because it's difficult to type, right? So you can have the single code. It also represents the lot. Okay, for hardware operation. Okay, how about the OR sign? OR sign, we use the plus sign. It represents OR. But when we pronounce this, don't pronounce plus. Use OR to represent, okay? Yeah, this one, for more technical or more professional, you usually use this symbol. This symbol, that means union. Union, that means, yeah, your things is A's things is B's things. B's things is A's things. Got it? Okay, it's a union. Okay, something like your mother's stuff is your father's stuff. Your father's stuff is also your mother's stuff. Although the real situation it may not. Okay, your mother's stuff is still your mother's stuff, maybe. Okay. Okay, and also the third one is called A dot B, right? But we don't call it dot. We call it N, A N B. Okay, so this one we call it N. Remember, this is a union. This is an N side. Got it? Okay. But what about the usage of N? That means you are going to have the intersection. Okay, intersection. For example, you have many interests. For example, your interest is is kids with elderly. Okay, maybe it's your interest, your hobbies. And you find another guy, maybe another girl, another boy also have this interest, kids with the elderly. Okay, so that means if you both of your interests end together, and the result is kids with elderly. Okay, so when you're chasing some girl or chasing some boys, we usually need to find out the common interest in order to have a better communication. Got it? Okay, so once again, this one we call it lot. Okay, and now we have the f, that means a function. After we lot it, so we have the function output. Okay, so for example, a is the input. Originally is 0. After lot it, it becomes 1. A originally is 1. After we lot it, it becomes 0. Got it? Okay, when or where we can apply this? Think about this in the toilet. For example, for the disabled toilet, you have the toilet lock. Okay, if there is no one inside, 0, no one inside, so you enable. Okay, that means the lock is 0. That means haven't locked. So people can enter. Maybe the LED, the sign, the signage, the LED signage display something. So you can enter. Okay, it becomes 1. If it is already locked, so the signage don't show the color, so no one can enter. Okay, it's easy. Okay, how about the or? Or is something like A or B. Okay, we have the function output. So if this one should be equals to A or B here. So A, B, we have the function output. So yeah, for or operation it's easy. Either one is okay. Okay, for example, of course both no. The result is no, but A is no, B is yes. Okay, so because either one is okay, so the function will also be yes. Okay, how about this one? If both are true, of course it returns true. Got it? Something like the DSC and the H. What was that? Okay, this is the truth table that where the Open University will accept you. The requirement of Open University is that your DSC result is greater than 20 or your age is greater than 21. It's okay. So let's see this case. Your DSC result is not greater than 20 because it's false. Okay, false. But yeah, your age is greater than 21. So you can still enter Open University. Got it? Admit. Remember last time I have a friend, yeah, he lived in Yunnan. Okay, he has many business in Yunnan. Okay, something like a tutorial center or yeah, I don't know what it is. And but his academic level is just primary school graduate. So how come he can teach others? No, he doesn't teach. He recruit some guys to teach. But when he applied for the Open University, they said that, oh, you're very suitable. Okay, because his age is greater than 21, no matter how the qualification is. Yeah, it's cute. Okay. Okay, how about the next one is AND operation. AND operation, that means both should be true. Both should be true in order to get true. Okay. If either one is true, it's no use. Got it? A is false, B is true, it's no use. Got it? Something like you get married with others. Okay, you agree? Yes, I agree. Okay, both should be agreed in order to get married. Got it? Okay, so let's see here. Yeah, something like for the plug. Okay, we have the live cable here, live pin, and also neutral pin, and it should be both should be turned on and okay, both should be collected and in order to light on the devices. Got it? Either one is not okay. Okay, so I think it's very easy, right? Okay, so let me use a Venn diagram to let you know what's going on for this. Okay, Venn diagram. Here, we have something that I need you to know is that, first of all, we have A and B. Sorry, A and not A. So what will be the result for this? Because A is over here. How about the lot A? Lot A is all other region in the scope. All other region in the scope. So it becomes, if this one and this one, because they don't have any overlapping area, so the result should be 0. Or we call it false. Got it? Okay, another one is that how about and? How about or? A or not A? Okay, because your stuff is his stuff is your stuff. So that means for graphical representation, that means include all. Okay, so that means it should be all the region. So it should be equals to 1. Got it? Equals to 1. 0, that means nothing. Okay. All region, that means equals to 1. Got it? And yeah, remember, AND operation. That means in the graphical world is an overlapping area or what we call intersecting area. For example, A and A overlap A, of course, is equals to A. Got it? A and 1. Because the overlapping area of A and 1 should be only A. A and 0. A and nothing. Okay? So A and nothing, you don't have any overlapping area with nothing. So it should be 0. Got it? And A and B, of course, equals to B and A. This is what we call it reversible. Reversible, okay? And A and B bracket, and further, and the C is also equals to A and bracket, B and C working first. Got it? Okay. Okay, so let me guide you this. Yeah, this is the whole circle of the green one, is what we call the A. The whole circle of the blue one, we call it the B. And the overlapping area, of course, this is A and B. But I would like to let you know about what is the green area left over here. Why I call it A and not B. Okay, so let me guide you like. For example, you do something like, now this is A, right? This is A. And then up to here, I don't want to include B anymore. So I do something like what? I go back like this. Okay, I go back like this. And so that means it won't include a B. So that means for this one, I call it A and not B. Got it? And same as the right one. So that, or in order to let you to have a better knowledge, a better memory, I call it to left pattern. Okay, this is left pattern. Yeah, if there are some guys in front of you, you can look at his or her pen to imagine. Okay, how about the right one? It's also the same. So starting from here, it is B. It is B. But when I coming to the intersecting point, I go to A. So we call it B and not A, and we call it right pattern. Okay, so use illusion or memory, your imagination to study this subject. Okay, so if this is left pattern, this is right pattern. So what you can imagine A and B. Okay, so what you can imagine. Yeah, of course. Perfect. It's a leaf. It's a leaf. Okay. 樹葉 is a leaf. Okay. Yeah, very good. And if someone asks me about what about the white area over here? White area is the scope. Okay. The scope. For example, in Hong Kong, maybe there are not just male or female. Okay. Maybe there are some alien here. Okay, they are not human being. Okay, so for those guys, it's also existing in the world. We can occupy the right area. Got it? Or we simply call it lot A or lot B over here. It's the scope, what we are going to tell. Got it? Okay, so yeah, so we call it the leaf. It's fine. Got it? Okay, and okay, let me stop here. Someone would like me to show. So the whole page, right? Okay, so let me. It's just nothing I have written, I think. Okay. Okay, it's just not much thing I have written. Okay. And here and this here and this here. Why I can listen to my voice? Why I can listen to my voice? Okay, weird. Okay, weird. Okay, finish. Okay, finish. Okay, next part I would like to share with you. Is the OR operation. Okay, so let's see. So yeah, we have or that means union. It's quite well, I can listen to my voice. It's so weird. Yes. How about now? No already? There is echo. Yeah, it's weird. Is it someone feedback your voice, my voice? if it is skewed. Okay. Okay, got it. Okay, next part for the OR operation, the union. Okay, let's see how can we work out this. I think it's easy. A or A, of course, is equal to A. Got it? And then, once again, the scope is over here. This is the scope. That the whole region should be equals 1. If all the region you cover in this rectangle, that means it's whole region, that means equals 1. And A or 1, or because union, that means your stuff is also my stuff. So A or 1. 1 is all stuffs already, so it should be equals to 1. A or 0, yeah, A or nothing. Okay, for example, someone told you that I don't have anything anymore, okay, something like that. And you said that you have me, okay? So that means A or 0, so you have A. Easy. Okay, A or B is also equals to B or A. Once again, A or B bracket or C, the sequence is not important, so it's also equals to A or bracket B or C. Got it? So once again, if I draw 2 circles again, and I would like to mention A or B. So, do you know which region I'm talking about? Of course, it's whole region. Whole region. This is A, this is B. The whole region, that means the whole pipette. Whole pipette. Yeah, this one is whole pipette. Got it? Easy. Okay, so okay, so let's take a look. Yeah, more. Remember, this one we call it union, or we call it OR. Okay, so let's think about the distributive properties. That means something like you multiply the A into the bracket 1 by 1. So that means it becomes A and B, or A and C. Okay, it's easy. How about this one? It's also distributive law. Okay, so C multiplied with the A, or C multiplied with the B. Got it? It's finished. And then how about absorption property? So this one is cute. Okay, before I talk about this, okay, let's see some of the real relationship. Okay, you may interest. I just copy from the web. Okay, so for example, this one is what you love, but it's also your friend. Okay, don't know your friend is occupied by others or not. Okay, so if your love and also your friend end together, okay, these are complicated things. Okay, these are very complicated things. Got it? And also, for example, like, yeah, if it is sex and this is love, yeah, or you are adults. Okay, so maybe because for some secret you don't want to tell your another half. Okay, so maybe it's couple, maybe it's a perfect match. Okay, you imagine this one. If you're sex and it's your friend, that means you are sex with your friend. So it is, I don't know what does it mean. Okay, you can imagine. Okay, but if it is you have love and also you have friendship, you have the sex all together, all these three overlapping area. So this is what we call perfect match. Yeah, hopefully all of you can find this niche region in your whole life. Okay, got it? Okay, not just this. Not just this. Okay, thank you. Okay, thank you. Yeah, it's more my wish. It's more important than the course. Yeah, you study well in this course is no use. But if you find a perfect match area, you can be yeah, happy life. Okay. Yeah, it's a good example, I think. Okay. So think about this. Okay, and then next one is the absorption property. Okay, for example, this one is A or B. A or B, right? So A or B is this one. And you are using the A. You are using the A and this whole pipette. A is this one. And the whole pipette. So can you imagine? Can you imagine? That means it should be the A. So A and A or B, it absorbs the B. Okay, so it doesn't need to include the B. So we call it absorption property. Got it? Okay, so remember this is acute. A and A or B. So it becomes A only. Got it? Becomes A only. And how about this one? A or A and B. Okay, let's see A and B first. A and B is just the leaf. Remember, it's just the leaf. So A or A and B. Because it's or. Your thing is my things. Your stuff is my stuff. So it becomes A also. Okay, this is a very famous, what we call absorption property. Got it? Once again, you and you or others equals you. You or you and others equals you again. That means in your world, it's only you. Okay? Treat yourself the best. It's the absorption law. That means forget others. Okay? Remember. Okay, the most important laws is coming. What we call this is one of De Morgan's law. Okay, we usually examine on this law. Okay, let's see here. Not A and B equals to not A or not B. Why? Okay, let me introduce the concept to you graphically. Okay, first of all, not A or B, sorry, not A and B, that means it's not the leaf, right? A and B is the leaf. So not the leaf, that means the blue area over here. All other region except the leaf. Got it? That means whole this region. How about lot A or lot B? Okay, let's see here. Lot A is this region, right? And lot B is this region. If I or together, that means include all. Include your blue region and also my blue region. So it's also become this. This is what I call it De Morgan's law. It's okay. It's interesting. Okay, so after I graphically prove this, it works. Okay, how about, yeah, so once again, or that means include all area. So it becomes this. Got it? This is not A or not B. Okay, how about the right one? Yeah, once again, this one, A or B, not. That means not pipette. This one is whole pipette. Can you imagine? Whole pipette is A or B. Now remember the shape can let you to think faster. Got it? Whole pipette is A or B. And not it, that means the blue area over here. Can you see that? Okay. So what's more is that if I, yeah, this is not A, this is not B, right? If I AND together, not A and not B, that means the blue area and together, right? The blue area and together. That means we're going to find the overlapping area of the blue area of these two shape. Okay, so it becomes this. So it also get the same result like this. Got it? So remember, N, that means overlapping area. This blue area overlap. Okay, it becomes this. We just count the overlapping area. Okay, that means both areas should have blue in order to get this. Okay, so it also works for this. Now I would like to tell you how to remember the De Morgan's law. It seems that it's difficult, right? No, it's not difficult. Okay, let me show you what is the tips to remember. Okay, it's easy. Every time you see the long bar, so what you need to do is to separate the bar into one by one. Okay, if there's a 2 entity, you separate into 2 bar. If it is 3 entity, you separate into 3 bar. Okay, and the next one is that every time you see dot sign, or every time you see plus sign, it becomes dot. Every time you see dot sign, it becomes plus. And you can make it done. Once again, let's see here, a long bar into 2 separate bar. A dot sign becomes plus sign. The same as this one, long bar becomes separate bar, and plus sign becomes dot sign. Okay, it's easy, but it's powerful. This method is powerful and interesting. Got it? So let's see further. Okay, example 1, simplify this expression. Okay, so let's see. First of all, we treat this one to be the first thing, this one to be the second thing. Okay, and can you see we have the long bar here? So once again, long bar into two separate bar. Okay, and then dot sign becomes the plus sign here. Okay, easy. Okay, this is the first thing. Okay, the second thing is coming. Yeah. After that, we have duplicate to we have double bar here. Okay, so double bar becomes cancel. Not become cancel. And once again, this one have long bar here, right? So by using De Morgan's theorem again, becomes 2 separate bar, 1 separate bar, 2 separate bar, and plus sign becomes dot sign. So okay, and the plus sign direct copy. And once again, there's a double bar here. Every time you see double bar, cancel out. Okay. Okay, what's more is that yeah, double bar cancel out, double bar cancel out, and then this is a plus sign, and yeah, you just eliminate. You just don't write the dot, and then you can have the result like this. Okay, this is the final product. It's the final solution. Okay, got it. In the examination or in the assignment, if you fail to work out the simplified form, we cannot give you marks. Okay, so your ultimate goal is to make the simplified form, because only the simplified form can let you to use the least hardware. Yeah, number of hardware you need to use is the least. Okay, got it? No, if you still leave the dot over here, of course it's still correct. Okay, I just means the number of terms and also the bar should be exactly the same. Of course, for example, this one put to the left side and this one put to the right side, of course, it's also fine. You put the dot in between is also fine. Yeah, no dot or having the dot it's no difference. It will also give you correct. Okay, it will also give you full marks. Okay, example 2 is coming. Okay, once again, simplify this. We have f here, function here, equals to this. And what we're going to do is that long bar into 2 separate bar, like this, and plus sign becomes dot sign here. And yeah, you have a double bar here, so you cancel. And also you also have double bar here, cancel again. So it becomes this. And then what we're going to do is a distributive law. Okay, you multiply this one to the bracket one by one. So first of all, you multiply to the A first. You have AA bar B. And then you multiply to the BC. Okay. Yeah, because of this, A times A, of course, also equals A. So you can absorb one of the A. Got it? And when you multiply this one into BC, you can see that B, you are not really going to multiply one by one. You extract something interesting. B and not B. I've told you that B and not B is nothing. Okay? B and not B is nothing. Got it? So it becomes 0. Remember last time I showed you B and not B. That means A and A is A. A and not A is 0. It's nothing. Got it? Okay. So this is the case. Got it? I think it's easy, right? Okay, this part is finished. Hope you got it well. Okay, here we go. We have the third part. This one is what I call it basic principle of MOSFET. I think it's a quite difficult part for you. Okay, so let's see how can we make it done. Okay. Okay, first of all, we have the voltage control device called MOS. Okay, and MOS, that means a metal oxide over here. Got it? Metal oxide. Yeah, we have the oxide layer, okay, over here. And then we have the both NMOS and PMOS, okay? Yeah, and for this one is the metal oxide. This is what we call insulator at the gate. That means no current can pass through this because it's oxide. Yeah, made of a semi-conducting material, of course. Good, semi-conducting material. And so every time we provide the voltage to the gate in order to absorb some of the channel, to form some of the channel. Okay, let's see what is inside the NMOS or PMOS. It's what we call this silicon. Silicon, you always discover this where, okay, you sometimes, yeah, when there's a girl, he would like to make her breast a little bit thick, they would like to employ the silicon, okay? But also in the semiconductor world and in the hardware world, we usually use this. Yeah, silicon. Have you ever heard Silicon Valley? That means all the chipset, all the CPU, all the chipset are made by the semiconductor, and silicon is one of the main components. Okay, so for example, I would like to let you know how the MOSFET works. Okay. Yeah, in fact, if I provide the electricity to this, it can work. But what I would like to let you know is about the doping. What the doping is about. Doping, that means you inject something inside the silicon or the semiconductor. For example, if you have studied chemistry before, you know that there are, okay, like here, we have some of the element, they have the hand to hold some electrons and share the electron with others. Okay, this is what we call it covalent bond. Okay, so if it has 8 electrons altogether, okay, so it becomes stable. So that means every hand over here, they are holding 1 electron and share with another atom to share the electron. That means they are holding hand heavy. Every pair of the hand, they have 2 electrons altogether. Got it? Okay, think about this. In fact, they are stable. But what does it mean for doping? That means they would like to inject another type of atom, like this one, to replace the original one. Once again, they would like to, yeah, put this one. Okay, let's see here. This guy not only have 4 hands, it has 5 hands. So the available hand over here are really welcome to accept electron. Okay, are very welcome to accept electron. Okay, so if it is a case, so when there's an electron come to this doped semiconductor, it's welcome. Okay, so that means the electron can come from somewhere to put it to here. Okay, or from here to give it out. Got it? Now this is what we call n-type doping. Okay, because it can provide more electrons to others. Okay. Okay, another type is that let me guide you like, for example, this blue one, I can say that is a p-type doping because it has hand over here, but it doesn't have electron to give to others. Just now, the atom injected this have 5 hands, so it has 5 electrons. It has 1 electron more, so it can given out electricity. It can transmit the electrons to others. But now for p-type doping, we dope another atom which has a less electron over here. Okay, so that means it has a hole here to accept incoming electron. Okay, so this is what you need to know. We have p-type and n-type. Okay, so let's see here. We have hole to accept 1 more electrons. Got it? So that means n-type inside the semiconductor, it has a more than enough electron to go somewhere. And for p-type, it has less electron, but it has hole. It has hole to accept electrons. Okay, got it? So the principle of conducting electricity is not like the metal. Got it? For metal, that means they would like to transmit the electron out, okay, through the cable, okay. But for semiconductor, they accept the electron by using the hole to get it. Got it? So let's see the difference. So for example, this one, N-channel MOSFET, we call it NMOS. We have a N-type doping over here, and the substrate. Okay, this is N-type doping. We have both, and the substrate P is over here. And this one we call it lightly doped for the N-type, and then for the substrate, this P-type dope. Okay, so I would like to introduce one thing called depletion layer with you. What does it mean for depletion layer? Okay, let's see. Yeah, I just zoom in the junction over here. Can you see that? For the junction between the substrate, okay, the blue one is the substrate, and the doped region. Because this one is a N-type doping, it have many electrons. Okay, so it will automatically go to the hole to form this depletion region, because both of them would like to be comfortable. Something like, yeah, a boy, okay, you would like to give out something. And something like a girl, yeah, it has a hole to hold something. Okay, so they would like to, yeah, it's naturally, they would like to give out something from the boy to girl. Okay, got it? Can you imagine? What I'm talking about is, for example, your father has some money to give out, and your mother has a pocket. Pocket is a hole to hold the money. Okay, so both are welcome, both feeling comfortable. Got it? So once again, you can see that. Yeah, the electron from the N-type doped is coming to the hole in the P-type dope automatically. Okay, it's laterally. Got it? So it's easy. So after that, no hole over here in the boundary. Okay, in the boundary. So it becomes a depletion region. Got it? Okay. Yeah, can you see that? Once again. Yeah, the electron is coming to the hole laterally. Got it? Easy. So, and the central region has canceled out electron and the hole. So it becomes depletion region. Got it? We use orange color to represent. That means there's a cancel out the electron and the hole over here. Okay. So the real world, when I collect the battery over the whole part, over the whole NMOS over here, you can see that because the positive region, the positive polarity is collected to the gate, which has the oxide. This orange area, above the orange area is the oxide. So oxide cannot conduct electricity, but it can attract what? Because it's positive, it attracts some of the electron to come. Okay, can you see that? The pale blue electron is coming. Okay, so yeah, once again, because it's a positive pole over here, and the backside of the battery is collecting the bottom part of the substrate. Can you see that? Collect the bottom part of the substrate. So it has a E field over here, electric field over here. So the positive gate, the electron, once again, the electron will go to the positive gate automatically. Got it? Because the electric field has set up. Okay. So yeah, let me zoom in. And then more and more electrons form it here. It becomes a channel for these two n-doped area. Okay. Then these two n-doped area becomes conductor. Okay, because you line up these two. Originally, these two doped area won't collect together. Okay, but now after the N channel is formed, they collect with each other. So they can this channel allow these two doped region to have electron flow. Got it? It's important concept. So let me guide you what is meant by source, drain over here. So after the channel is formed by the gate, once again, after the channel is formed by the gate, that means these two doped area can conduct electricity. Okay, so if I give one side to be the, I collect another battery, one side to the positive pole, we call it drain, one side to the negative pole, we call it source. Okay, once again, I collect this side to the drain and another side to be the source. So the current will pass through from drain to source because of another battery. Got it? Once again, we have two power source. Got it? So yeah, this is the working principle of NMOS and also PMOS. Okay, hope you know what I'm talking about. Okay, so get back. The drain and the source is over here. The drain is above, the source is at the bottom, and the substrate is over here. Got it? In this one, the source is above, the drain is at the back. Okay, it reverse for P channel. Okay, so yeah, once again, yeah, the gate and the substrate connect to one power source, and the drain and the source connect to another source. Got it? Okay, so for n-doped, that means n-doped region. That means electron numbers increase. So that means over here, electron number increase. Okay. And number of electrons should be greater than number of holes. Yeah, we seldom use a positive. Okay. So I mentioned that number of electrons is a greater number of holes in a semiconductor. Yeah, for n-doped. How about p-doped? That means number of holes is more than the electrons. Okay, so number of positive, that means number of holes is greater than number of electrons in this semiconductor. Got it? Okay, so the next part, I would like to let you know about the working principle of this. When the VGS equals to 0, okay, VGS, that means the battery collect through the gate and the substrate is equal to 0. Do you think that it will attract some electron to form a channel? I don't think so, right? I don't think so. So that means no channel appear because the VGS is so small. It's smaller than what we call it V threshold. V threshold, that means it's the minimum voltage that can make the channel form. Got it? So we call it not enough attraction to form a channel if a VGS is too small. Okay, no channel form, and then the drain and the source cannot conduct electricity. So what I can say that, yeah, because of no channel form, so the ID, what is ID? The current from the drain. The current from the drain is 0. And I can imagine the drain and also the source is open and it's infinite resistance over here. Okay, when you collect something from drain to source, it becomes infinite resistance. And I can set that if you treat this to be the switch, it becomes open. The switch is open because of infinite resistance. Got it? Okay. And so we make use of this in the cutoff region. We call it as a cutoff region. Okay, no channel form. So when you collect something from drain to source, it becomes open. Okay, how about another one? Is that, okay, bottom left, when the VGS is greater than or equal to V threshold, the channel is formed. When the channel is formed, so let's see. When I collect the source to the substrate or to the ground as well, okay, because of channel is formed, so the RDS is not infinite anymore. So we have the ID, but the ID is increasing. Increasing, is it good? For analog world, it's good, but now we are going to have digital. Digital only have 0 or 1. Got it? Increasing, small current, is it acceptable? You treat it 0 or 1. It doesn't make sense, right? If we want to have 1, we should have maximum current. Okay? If we want to be 0, we should have a current that is 0 or a little bit more than 0. It's fine. Okay, I would like to illustrate this form later. Okay, so that means if I put a drain to a battery, to a power source, it has a current flow. And we can call it the switch is closed. Once again, why I need to introduce the NMOS or PMOS, because I would like to let you know, I would like to use these two things to become switch. In digital world, switch is important. Okay, so once again, when DGS is VDS is increased, RDS is come to be smaller, okay, and the ID is increased. This is what we call linear region. But in digital world, we don't want to have linear region. What we want to be is the saturation region. When the VDS, that means when the drain to source voltage is greater than VGS, more. In many cases, the resistance between these two and the region becomes minimum. So the ID current across this is the maximum. Okay. So when I detect the ID is maximum or almost maximum, I treat it to be digital 1. When that means we usually use the saturation region. We don't use linear region. How about 0? Just like for before, if it is at the cutoff region, almost no current, almost 0 current, or ID is the minimum. We use it to represent 0, represent digital 0. Got it? Okay. Remember, digital don't use linear region. Okay, you can write down. Okay, how about the PMOS? Yes, I think the PMOS is almost similar, like here. Because of PMOS, we want to have the channel for P channel. P channel, that means it's full of hole over here, full of hole for the channel. So we need to apply the gauge to be, should be okay, should be, oh, yeah. Okay, so that means, because we are going to form a channel of the P channel, so that means we should have the VGS should be very small. Okay, but now the VGS is equal to 0. It's still no channel form. Why? Because the V threshold now is negative. The V of the gate should be negative number, should be more negative enough to attract or to repel the electron to form the P channel under the gate. Okay. Remember, for NMOS or PMOS, when VGS equals 0, it also at the cutoff region. The switch is also open. Got it? And remember, in order to form a channel, the VGS should be more and more negative than V threshold. Just now I circled the V threshold is negative 0.7, right? Negative 0.7. Okay. So once again, let's see here. When the VGS is much smaller than V threshold, much smaller than or equal to negative 0.7, okay, so it attracts more hole over here, more hole over here, okay? For simplicity, you treat it to be positive charge, but it's not the case. Okay, you repel the electron, think about this. So the P channel is formed. So when I collect the source to be the positive and the drain to be the negative based on the power source, so the current will pass through from source to the drain. Okay, current will pass through source to the drain. Remember, the current pass is reversed. Just now in the NMOS, it's drain to the source, right? But now it's from source to the drain. Got it? Source to the drain. Okay. So once again, R decrease and ID increase, so the switch is closed. But once again, we are not going to use linear region. We are going to use the saturation region. That means VDS is much more negative than the VGS to make the RDS minimum and the ID to be the maximum. Got it? I think this page is difficult. This page is difficult, but it helps you to understand also the analog circuit as well. Got it? But now I'm focusing on digital part. Okay, finish. Oh, sorry that for my lesson because I would like to always teach you more. So I seldom have the break. Sorry about that. Very sorry. Okay, so let's see. I think you can. I think I'm giving you a hard time, right? Because I don't want to stop because it's an important concept. Really sorry. Can you hear some of the song it's playing? Okay, let me close the door. Okay, good. You cannot listen some of the songs. Someone is working on the renovation, I think, but you know that they always play the song when they are working. Okay, it's good that you cannot hear. Otherwise, it's disturbing you. Okay, here we go to represent those MOSFET to you. Okay, first of all, you have NMOS and the PMOS symbol, right? Okay, so let's see here. This is the NMOS transistor symbol. We have 4 terminal, drain, gate, source, and substrate. Okay. In many cases, we seldom mention the substrate. Okay. So sometimes we don't draw it. And because we have analog circuit and also digital circuit for you to learn, yeah, this symbol is for the analog circuit. Okay, we have the arrow letting you know the current flow direction. Okay, and the right part is the digital circuit. Got it? The right part is digital circuit. Yeah, we are no need to let you know about the current flow, but of course you know it already, right? Remember, for NMOS, the drain is at the upper area. Okay, upper area, usually upper area. We won't reverse it. Okay, drain is at the upper and source is at the bottom. Okay. Okay, how about for PMOS? For PMOS, once again, we have the analog version that the current pointing from the source over here. So this is representing the ID. Yeah, the ID flow, the flow of the current. And we usually, for analog circuit, we have the arrow. But for the digital circuit, we don't have the arrow over here. Can you see that? But how can we represent these two? Maybe you think that, oh, I know that the source is putting on the top. No, it's not the case. Of course, for PMOS, it's a common practice for putting the source at the top. But in digital world, we usually representing the PMOS by using the circle besides the gate to represent this is PMOS. But it doesn't need to have in analog circuit. It's only applied in the digital circuit. Okay, remember the symbol that you are going to use. Got it? It's important. Okay. Okay, so what I would like to let you know next is that how can we use the MOSFET switch? Because just now I have mentioned they can be work as switch, right? To become an inverter. Inverter, that means a LOT gate. Okay, let me guide you. For example, we have, in order to provide electricity, so I'm doing something like we have the on-off to collect the battery. So first of all, I have this setup. And if I collect the gate with V off, that means the VGS has a 0 voltage, right? Which is a smaller than the VT. What is VT? VT is reversal. So what does it mean? VGS, that means the potential difference between G and S. So you need to minus 2 potential. Now VG has a potential 0, and VS also has potential 0. So they are talking about the same thing, same potential. Okay, 0 minus 0, so we have 0. It's smaller than VT. So we can say that the RDS is infinity and V out is okay, and the V out is should be equals to the original VDD. Why? Because no channel can be formed over here. So we don't have the current over here. So the VDD is directly connected to the V out. Because of no current, so the V out have almost the same potential as VDD. Got it? No current. That means no need to waste the electricity. So V out is also equal to VDD. Got it? So that means I'm calling it simply the switch is opening. Okay. Once again, we treat this NMOS to be the switch. It's opening. And how about the value of V out? The value of V out should be very high, right? So that means when you are given 0 voltage, when you are giving, because it's off that means connect to 0, right? And then the output will be high. Or you imagine that you collected the low voltage and then the output will be high. It is inverting, it is doing the LOT operation. So it can become a LOT gate because of this. 0 input or low input, LOW, low input, and high output. So it's a LOT gate. V in is 0 and the V out is VDD. So it's inverting, so it's called the LOT gate. Okay, how about another one is that now I pop the gates into the V on. That means, for example, I give it is a high input. Okay, so after that, you can see that what is the value of VGS? Is VG is VDD, VS is 0. So it must be greater than or equal to VT so much. Got it? And okay, let's see. Because the channel is formed because of the high gate to source voltage, so that means the RDS is minimum, right? RDS is minimum. So for example, this is for example, the RL is quite large, it's something like 10 to the power 6, and the NMOS channel is only 10 ohms over here. So the V out becomes very small because most of the voltage is being displayed by the RL. It's only very few voltage left for the NMOS. So the V out reading is very small. Once again, you have a very high V in, very high input, but V out is almost 0. Very high input, but you have a low, LOW, low output. So it's also inverting. It's also doing the lock operation. Got it? And same as for PMOS, switch over here. First of all, I collect the VDD to the gate, and then I collect the source also to the VDD. Okay, if it is a case, what we're going to do is that VDD minus VDD is equal to 0. 0 is greater than the negative threshold voltage, negative 0.7, so it's also turning off. Got it? Also turning off. Okay, so now let's see the V out. Because the V out is collecting to the ground, 0 volt. And because of no channel can be formed, so the V out cannot collect to the VDD. So that means the V in is VDD, and the V out is almost 0. So that means high input, and then the output is low. Got it? So it's also inverting. Okay, how about the next one for PMOS? It's also the same. For another case, if I put the VG to the lower location, so what we're going to do is that we are turning on this. Okay, because we collect the VG to the ground, but the VS is VDD. So that means it's 0 minus VDD. 0 minus VDD is VGS. Okay, so it must be smaller than or equal to VT. Got it? So that means the channel can be formed over here. So that means we have the VDD connected to the V output. Okay. So that means, there's a typo. So RDS is minimum. RDS is minimum. So that means V in is almost 0, but the V out is being high voltage. Got it? So these two explanation is to let you know about how can we work out the inverter, that means the LOT gate, by using NMOS or PMOS alone. Got it? But I would like to let you know is that it's not quite desirable. Why? Because we are using a very large value of RL. Something like just now I used a 10 to the power 6 ohm. So it occupies a very large value, a very large location in the chipset. That means in the chip, semiconductor chips, it becomes a very large area. It's not desirable. Okay. So if it is a case, what we're going to learn is that can we think about some method to eliminate the usage of the resistor, because it takes up so much space in the chipset. Because in the integrated circuit, what we're going to have is all the things are very small. Got it? Okay. Now I'm talking about the IC design, integrated circuit design. Okay. So the solution is by making use of the CMOS inverter to work it out. Okay, CMOS, in fact, C, that means complementary. That means we use both NMOS and PMOS in a pair. So as to, first of all, you no need the large RL anymore. No need large RL anymore. And so as to reduce the power consumption. what's more is that it's quite efficient to fabricate. That means to make the CMOS than just NMOS or PMOS. Okay, let's see. For example, this is PMOS, and the left side we have NMOS. Okay, and you can see that we don't have the N substrate over here. So in order to make the PMOS out, we make the N well. You see that? We make the N well over here to pretend to be N substrate. Got it? So these two, that means NMOS, nearby the PMOS. Together, we call it CMOS. I think all of you have heard the term CMOS in something like the camera, okay, the lens, or the technology that's used to sense the focus is the CMOS technology, right? Yes, we usually use this is in the motherboard in order to save electricity, and also to fabricate the CMOS is much cheaper than the resistor because it only occupies a very small chipset location, very small area. Okay, let me guide you how to work it out by using CMOS inverter rather than the PMOS, rather than the NMOS alone. Okay, so let's see. Okay, this is a schematic of the CMOS inverter. Schematic of CMOS inverter. When we give the 0 voltage to be the Vin, okay, remember for CMOS inverter, PMOS is putting above. Can you see the circle besides the gate? And NMOS is putting at the bottom. Okay. So if I give 0 voltage over here, you can see that both, which one is turning on? Okay, let's see the VGS. For the VGS of PMOS is 0 minus VDD. 0 minus VDD. So it becomes negative voltage over here. Okay, it's a very negative. So PMOS is turning on. Okay, so the ID is passing through from VDD to Vout. Okay, that means a channel can be formed over here. So the Vout becomes very high voltage. How about the NMOS? Because the VGS for the NMOS is 0 minus 0, so it's also 0. That means VGS is 0, it won't switch on the NMOS. So the NMOS is closed over here. Got it? NMOS is closed over here. So it seems like it has a very large resistance over here, right? So that means Vin is 0 and the Vout becomes high. So it's inverter. Okay, once again, for PMOS, we have the channel form, but for NMOS, we don't have channel form, so the Vout becomes VDD. Okay. Okay, so it is simulating the, it's simulating this circuit, I think, this circuit. Okay, a very small resistance of PMOS at the top, and this is open. The channel is open for the NMOS. For this. Okay, how about the next one over here? Okay. Vin becomes VDD now. And take a look on, that means the input is high. Take a look on the PMOS VGS. It's VDD minus VDD. So it becomes 0. And how about the bottom? VGS is a VDD minus 0. It becomes VDD, which is much higher than the VT. reversal. So the channel is formed over here. Got it? If it is the case, so it collects the V out to the ground. So we call it pull down. We call it pull down. Pull the V out to the ground voltage. So we call it pull down NMOS. Got it? And this one, and for V in equals 0. So we put the V out to the up, okay, to VDD. We pull the V out value to VDD because VDD is upward, okay? So we call it pull up. So in order to remember the working principle of CMOS, we usually remember two words: pull up CMOS, pull up PMOS, pull down NMOS, and you can break it down. Okay. So once again, pull down NMOS, that means to collect the output to 0 volt. Pull up PMOS is to collect the output to the VDD. Okay, this is what you need to remember. So yeah, I think this circuit is simulating this one. Okay. Remember, for these two, we also have the situation that we don't have direct path between the VDD to the ground. So it can help save electricity, okay? Because we don't have the power dissipation in the resistance and the large resistor. Got it? So it's a perfect thing. Okay, thank you. So yeah, hope all of you can learn it well because it is a difficult topic. Okay, so I think in the future for lab one, you are going to do this to try some of the NOT gate operation on your own. Hope you think it's interesting. Okay, so it's finished for this part. Okay, finished. See whether you have any problems. Sorry for the overrun. Okay, I hope you like it. Okay, that's all. And I have put the previous video to the self-learning materials area. Okay, you know that? I think you know that, right? Okay. Okay, so over here, I have put the video, self-learning teaching video. Okay. And then the password should be my name, Frankie. If you don't know how to spell, it's over here. No worry. Okay, you just drop it. Over here is fine. And then you can see some of the videos are already here. Okay. Got it? Okay, I'm sorry that because some of the, because last time I haven't taken the video, so this video is not the most update, okay, but it's still fine for you, I think. Yeah, this lesson will be uploaded later soon, okay, because I think you think it's difficult, right? I'll probably try my best to explain as easy as I can. So maybe you can work on, yeah, watch more related video to absorb. It's much better. Yeah, yes, I think that all of you need time to absorb. Yeah, yes, of course, because for MOSFET originally it will teach you in the course beginning with 3. That means because this course is beginning with 2, ELEG 2201, yeah, for MOSFET. The working principle should be starting with 3 course. Okay, I'm teaching you something that is not the 2nd level, it's the 3rd level. Okay, I've tried my best, so you use it. Find your project. Okay. So I think in order to know the best, you need to watch more YouTube video that I demonstrate before, and take a look on my video again. Loop the video, sure. Okay. I think you no need to use the website to take the attendance anymore, because I've told you that I use the Zoom. Once you log in, it will automatically take the attendance by using the Zoom. You are trying my best to understand. Yes, sure. Thank you. Because you must understand. Why? Because lab 1 is coming. If you don't understand, you cannot work out the lab 1. Okay. Okay, so of course the course is coming to be more difficult. Okay. The first 2 lessons is just mathematics course. Everyone can teach you. No need to, no need to be so experienced teacher, I think. Okay. Okay, that's all. Thanks for coming. Okay, see you later, everyone. Bye-bye. Bye-bye. I need to take a rest. Okay. I still not have lunch yet. Okay, see you, everyone. Bye-bye. 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 Bye-bye.